Something strange is happening here. Recently, I have been concerning myself with Conway's game of life, the famous cellular automaton devised by British mathematician John Horton Conway. Specifically, I have devoted myself to exploring patterns that live on the 16 by 16 torus, that is, the top and bottom as well as the left and right edges wrap around to meet each other, which creates a bounded but limitless space. Admittedly, the 16 by 16 torus is a rather small space to explore in Game of Life. Many fascinating patterns need much more space to evolve, so I am aware that I have deliberately limited myself in the possible patterns I will see. While the space itself might seem small, the number of patterns I can explore is actually vast. And I mean vast in the astronomical sense. Literally astronomical. 16 rows and 16 columns gives me a space of 256 cells to work with. As each cell in Game of Life can be either dead or alive, we have two possible states for each cell, which totals to 2 to the power of 256 possible patterns. How many is 2 to the power of 256? Well, in standard scientific notation, that is equivalent to about 10 to the power of 77, which is a 1 followed by 77 zeros. How big a number is that? And what does that even mean? It means that we have about as many possible patterns on the 16 by 16 torus as there are atoms in the observable universe. Now let that sink in. I find this endlessly fascinating. There is literally a universe living on this small torus, a pocket universe for me to explore. My primary interest is to find Game of Life configurations on the torus that live for a long time. I explicitly exclude repeating patterns like gliders or oscillators. Once a Game of Life pattern repeats a previous configuration, I stop the simulation and count the number of generations it took it to reach its halting state. I have started collecting known patterns with high longevity and even named the longest runnings. After all, it took me a while to find them. So, how long can patterns live on the 16 by 16 torus? Is there an upper limit they cannot cross, or is it possible to find patterns of arbitrary longevity? There is this hypothesis in the Game of Life community, among them serious mathematicians and computer science researchers, that the generational count of a Game of Life pattern on a torus seems to be limited by roughly 5 times the available space. For the 16 by 16 torus, that would mean that the upper limit for longevity seems to be in the order of 5 times 256, which is 1280. And for quite some time, this hypothesis seemed to be true. I've been looking at patterns within this pocket universe for more than 2 years now, and the longest running pattern I managed to find lives for 1273 unique generations. I called it Ignis Draconis, the fire dragon. Recently, a fellow Conway Life forum dweller announced the discovery of Indicum, the new reigning champion of long-lived patterns with a generational count of 1285. So, the gauntlet was thrown. I picked up the challenge and tried to find an even longer running pattern. I've pivoted from running my search for long-lived patterns from browser-based code to optimized CPU parallelized code that I can run in the background. With the help of AI, I was able to get a program up and running that looks at about 30,000 Game of Life patterns per second. With this new Glyph hunter code, I made an astonishing discovery. Not only was I able to quickly find patterns that are even longer lived than Indicum, patterns with generational count above 1300, 1400 and even more are nowhere near as rare as I thought. The currently longest running known pattern, Oklo, has 1,884 unique generations and was found after looking at about 100 million patterns. This in its own right would actually have been a moderately interesting discovery, for it clearly disproved the hypothesis that longevity is bound by 5 times the space. But then something utterly bizarre happened.